Dr. Khurram Joya is an active researcher, innovator, mentor, speaker, and trainer. And currently, Dr. Joya is working as CEO and co-founder of Institute of New Horizons. And also, he is an executive director of AR Education Pakistan. Formerly, he worked as a faculty member at UET Lahore and also at King Fahd University of Petroleum and Minerals, Saudi Arabia. Dr. Joya received his PhD from Leiden University, Netherlands. Presently, he is having a research H index of 24 and over 325 impact factors, which contributes in authorships of many patents, books, chapters, and articles. Molecular and his research area mainly focused on molecular and functional nanomaterials, functional surfaces, and thin films, organometallics, electrocatalysis, electrochemical sensors, biomass conversion, and dye solar cells. His research accomplishment include several national and international awards. Moreover, Dr. Joya is deputy board member of Danish Electrochemical Society, and also he is editorial board member of many scientific journals. Let's welcome him for another intellectual lecture session today. Thank you. Over to you, sir.
Sadia, for very, very kind and detailed introduction. I still feel I'm just a simple and humble person and just, let's say, continuing my quest and interest in research and science, higher education, all those things. So let's directly start. Normally, I give lectures on my research and all those things, but I just formulate this scientific session in a different way, let's say, specifically for young researcher or PhD students, so they can learn how, especially in this field, how they can carry on their research, not maybe exactly in the same field, but let's say at least they get some inspiration or some guideline that how they can pursue their research in different fields within the umbrella of nanomaterials or functional nanomaterials. So what I will do that actually, as title is manifesting, so I will be focusing on, let's say, functional nanomaterials, and in a different way, I will discuss about their how to synthesize them, how to develop them, make them, and then some characterizations, and then of course some application. But of course, my research now more focused on application compared to characterization and development, because once you become a senior researcher, this synthesis and characterization, they are just complementary things. But of course, main thing is you develop a material for specific certain applications. Okay, so actually nanomaterials there are so many ways to, so many ways to conceive the word nanomaterials and functional nanomaterials. It can be based on their type or what those nanomaterials are in fact based on chemistry, and then of course it can also be dependent on what those nanomaterials are going to be utilized in what way they are going to be utilized. So what I did actually, I just divided this into three portions. Like first we discuss about the synthesis, then characterization, and few things about characterization, because I know many young students, especially in the beginning of their PhD or their research, they get confused that how they have to proceed their entire research project. So in general, nanomaterials are the materials which are present on the nanometer scale. I don't need to go into the details. They can be one-dimensional, or in many cases they are 2D or 3D materials also. And normally we call them functional or functionalized nanomaterials. Let's say more precisely functional nanomaterials, because they have specific property which relate themselves, the nanoparticles, those, to perform some specific applications. That's why we call them functional nanomaterials. And of course, these nanomaterials, because it's just dependent on their size, so they can be organic, they can be inorganic, they can be polymer material, and in many cases they can be hybrid combination of two, let's say, organic and inorganic. In some cases, organic, and inorganic as well. And of course, like I said before, there are so many applications where these nanomaterials can be performing functions. For example, catalysis, which is a electroorganic synthesis, or let's say electrochemical synthesis, electrocatalysis processes, also sensing, biomass conversion, in-situ spectroscopy, waste water treatment and drug delivery. Of course, the applications are much beyond this, but this is just because I'm going to more focus on these applications in my talk. So first, let's discuss about how to develop them. Like I said before, we are working on both type of nanomaterials. They can be organic, they can be inorganic. So in as far as, let's say, organic materials are concerned, we're working on developing some nitrogen-based or heterocyclic ligands. Then we just complex them with certain metals. In this case, you can see we complex these ligands with iridium and ruthenium also, and we develop, of course, a huge library containing more than 100 different molecules or complexes. And then, of course, we utilize them later on to perform certain catalytic applications. And of course, you can see in the below figure, we have just modified them, these assemblies, because the purpose was to switch them or anchor them or immobilize them on the solid surfaces. So of course, in many cases, you have to add some specific units with the molecules so that they can anchor strongly or adhere strongly to the surfaces where you want to perform certain processes. And of course, it's not so difficult to make organic molecules. If you go to the simple book of organic chemistry, let's say bachelor or master level, you will find so many synthetic protocols. But let's say simply let's say we can develop or take those materials just by simple extraction. In many cases, those molecules are present naturally. So naturally or even in unnatural way, but we just need to extract them. And then, of course, more precisely, if we talk about how to synthesize them, so there are different organic synthesis methods. For example, you can do direct organic synthesis, in which you just blend the ingredient together, and then under certain condition of maybe temperature, stirring, or catalyst, your product is ready, and then you just need to isolate it and purify it. Then there is another way you can make them, which is like, let's say, a new emerging field in organic synthesis, and it's known as click chemistry. In click chemistry, you just add a clicking agent and then ingredient, and then it's just a matter of click that the product is ready. Then, of course, if we talk about the trivial organic synthesis, so there are many oxidation and reduction reactions in organic synthesis, in which you can just obtain your product as a result of oxidation of the precursor or reduction of the precursor. Then, of course, we can also develop them by addition reactions. In addition reaction, you just add a certain unit or molecule to the already present molecule, which is in many cases precursor. And then, of course, we can also play around by using substitution reaction. So in which substitution reaction, you just substitute one unit with another unit to make your desired molecule. Then we can also prepare organic molecules by coupling reactions. In coupling reaction, normally two molecules having a coupling units just blend together under certain condition. So coupling can be, of course, homocoupling, in which both the molecules, the precursor molecule are same, or it can be heterocoupling. In certain cases, coupling can be between aromatic and aliphatic component also. Then, of course, we can also use a method known as cyclization. In cyclization, we just use this simple straight chain molecule, and then, of course, under certain conditions, it cyclizes to make cyclic compounds, for example, cyclic and as well as aromatic compound also in some cases. Then, of course, a very, let's say, big arena of the organic synthesis is Grignard reagent. So by utilizing Grignard reagent, you can make huge variety of organic molecule. Then, of course, recrystallization, like I said before, there are, of course, much more method beyond this list, but mostly we were focusing on these, let's say, in one or in some cases more than one from these techniques to make organic molecules. So, like I said before, in some cases you develop molecule based on how you want to utilize them. So in this case, you can see we develop these units, or we wanted to develop this unit because we want to put these molecules or immobilize them on the conducting oxide surfaces. So based on that, we develop this oxygen or oxy-based group like phosphonic acid and carboxylic acid, because they anchor very good to the oxide surfaces. In other cases, of course, I'm not using those examples here. We also develop molecule with thiol functionality, because thiol is very good if you want to functionalize your molecule on gold, platinum, or silver surfaces. Okay. Of course, in some cases, you don't need to develop a separate, let's say, units for anchoring, but you can just also use physical, let's say, parameters. In this case, we just use simple adsorption, and because these molecules are not soluble in water, so as a result of adsorption, molecules stay in some time in monolayer, close to molar, but of course, in some time it makes stacks also, because the organic, the aromaticity is there, which induce the stacking of pi phase stacking of the molecules. And once they absorb on the surface, once you put the electrode or the material in the water, aqueous media, let's say, they don't let's say leach out of the surface because of the adherence to the surface plus hydrophobicity of the water. So this is another way, let's say, simple physical way to put organic molecule. So now I move toward inorganic, which, like, let's say for last 6-7 years, most of my work is on inorganic functional materials. So inorganic material can be made by many methods, but I include again those methods which are mostly used by in our labs. Plus, of course, we develop those methods. Let's say we evolve those methods from time to time, depending on how we want to make different molecules. In some time, we change the conditions. In some cases, we change the precursor, let's say, material also, chemical also. In some cases, we even, let's say, use different conditions in which we are going to prepare those nanomaterials or nanoparticles. So in very beginning, we started to work on electro deposition. Then we moved toward anodization. Both of these methods are electrochemical method. In general, you can say in these methods, electrode potential or electricity is used to induce the crystallization or particle formation of the nanomaterials. Then colloidal thin films, you develop the colloids, and then under certain conditions, those colloids then condense and solidify on the surfaces as a thin films. Spray pyrolysis, you just use a spray on a hot surface, and then of course the temperature is normally 600 to 700 degrees Celsius. And then as soon as the spray reaches the surface, it just pyrolyzes the material, whatever is there, and normally you get the controlled oxide of the specific molecule, specific atom, let's say. Solid phase synthesis, in solid phase synthesis is a simple method. You just use, let's say, it's mostly used to prepare blend of or mixture of compounds. So you can use 2 or 3 ingredients, and then just you grind them together, and then of course you just anneal them, and as a result of this, you get a mixture of, let's say, a combined or a compounding effect of the 2 or 3 ingredients, and then in the other you get your compound, whatever it is, the desired compound. Molecular precursor method, actually in molecular precursor method, we use the organic molecules containing certain metals, and then as a result of, either you can use electrochemical processes or the heat treatment, and then those precursors containing certain elements or metals, let's say, can be directly transformed into thin films oxides or nanomaterials. The hydrothermal method is actually a very conventional method. Many people, many parts of the world it's practiced, and it's one of the most, let's say, utilized method in the lab. In hydrothermal, simply you just use the ingredient, and in some cases you use certain other chemicals to control the pH. For example, urea and citric acid, most of the people use, but of course you can use ammonia also and so many other things, depending on what kind of pH you want to have it. And then we just put all the mixture in an autoclave and put it under the furnace for a certain time, a week, 2 days, 3 days, and after that your desired product is more or less ready, and in many cases you don't even need to purify it. Then other thin film methods, conventional methods like CVD, PVD, they are, let's say, commonly used in many labs. Laser deposition method, most common is PLD, pulse laser deposition. And one of the projects I have done in the past also using pulse laser deposition method. Then of course ALD is like more controlled technique to make a very precise control thickness of the thin film. So ALD is atomic layer deposition. Normally in this technique, the material is deposited atom by atom, and it's a very controlled technique. So this is all about what kind of method to develop them. Then of course, either of these methods can be used to make these type of not only electrochemical material, but also photoresponsive material. For example, bismuth vanadate you can see in this figure, hematite or iron oxide, tantalum nitride, then tungsten trioxide, tantalum oxynitride. These type of material can easily be developed by using one or more of those methods I mentioned previously. And then what normally is, why we or many people are developing these films, these let's say materials, that you can use them as a photocatalyst to perform a certain application under the visible light. Because these are colored material, so you can see they have, let's say, shorter band gap, and because they are colored, so they can absorb under the visible range, which is roughly from 300 to 800 nanometer. And of course, in other cases, or in some cases, at least in our case, let's say, we are not using the powder, but we just develop the thin films out of these materials, these photoresponsive materials, and then we put on top another material, which is a catalyst. Again, catalyst can be organic or inorganic in our case, and then it can perform a photocatalytic application over certain, let's say, certain material. It can be photodegradation, even for for antimicrobial activity, or in our case, let's say it's for catalysis. Okay, so I will just a little bit go into each method one by one very briefly, very quickly. Let's say electro deposition method. In electro deposition, normally you use a metal ions in the media, and then again at the other function of electrode potential and pH, you can easily develop or deposit those thin films, which are in many cases nano pattern on the surfaces. You can see in this case we have this nickel oxide based actually nano hair, nano worms. And then you can see this is not very, let's say, crystalline film. It's like amorphous carbon dioxide film. And we developed this by using carbonate bicarbonate buffer system, in which we put the CO2 gas to maintain the pH close to 7, which is neutral. And neutral pH is actually very good to develop the oxide of the first order transition elements. Then anodization is another method. In anodization, what we did, we use metals and directly then put the metal in the electrolyte media without having the metal ions. And then as a function of pH and electrode potential, we actually controlled, or let's say on a micro scale, we etch the surface by our own will. And then of course, once those particles are leached out in the form of ions, as a function of pH now, they put back on the surface in the form of hydroxy oxide or hydroxide, you can say. And once you dry it, take it out and dry it, it becomes oxide. So you can see in this case the figure saying it's a copper oxide nanoliths we developed by this anodization method. And the bottom figure you can see the beautifully oriented nanoflowers of silver oxide, which we also developed by using anodization. Then colloidal thin film, like I said before, it just you develop the colloids under certain conditions, and then you just spray them on the surface to make thin films out of colloidal nanoparticle or colloidal thin film, let's say. So in our case, most of the colloids were made also by using this bicarbonate-carbonate couple, because the beauty of this carbonate-bicarbonate couple is you can control the pH at your will. So you can go from roughly from 6.5 to 10, even in some cases to 11, 12 pH by using more carbonate instead of bicarbonate. So you can switch over the pH depending on whatever particle you want to make a colloid, and even you can control the size of the same colloidal nanoparticle by just shifting the pH up and down. Molecular precursor method, we were working in the beginning with using different molecules, but in this case you can see we use this trihydroxy iridium CP star complex, which we just let's electrolyzed in under certain condition, and pH was close to 6, and then it made a with a very fine transparent bluish film on the electrode surface. But then later on we just changed this technique and worked more on the current rather than the potential, and then we were able to, let's say, convert this amorphous film into a very, let's say, highly crystalline film. And here you can see even in the part 5 the nanoparticle is obvious, which is close to 1.6 1.7 nanometer. Spray pyrolysis, it's a very easy and simple technique. Of course, it's something expensive, but it can be developed at home. At home means in the lab, students can develop it. You just need to heat the surface to a certain temperature, like I said previously, 600-700 degrees Celsius, and then you just controlled spray the precursor, whatever your precursor solution is, on the surface. And as a result of fine, let's say, because spray should be very fine, it should not be in the form of, let's say, big particles. Big, let's say, liquid particle. If the spray is really sprinkled fine and having fine particle and spreading everywhere smoothly on the surface, then as a result of heating, let's say, heated surface, those particles of the solution, they get pyrolyzed very quickly, and quickly you can develop the nanoscales thin films on the surfaces. Of course, there are a few conditions you need to set, but once you become mature, it's very easy to use these techniques. And you can see in this figure, we develop almost all the first order transition elements. They're thin film by using this this method. And you can see even the cross-sectional SEM images. You can see in most cases, the thickness of the film is less than 1 micron, which is very good. Then hydrothermal method, I said before that it's a very conventional method. In this case, we use this method to make metal chalcogenides for water oxidation also. So you can see in one example, we made this nickel oxide nanospheres. We also have developed copper telluride nanowires and cobalt telluride nanoflakes also. Then chemical vapor deposition, it's a simple, easy method also to make thin films. In this case, we developed thin films of palladium. Later on, we also move towards developing these films, developing CVD-based films of first order transition elements. And that paper is also just online, I think, for last week or so, something like that. You can see, so we develop different type of films. In this case, you can see nickel oxide, cobalt oxide, copper oxide, and iron oxide using CVD. Then, no, next is how to characterize them. So let's say anyone working on these three organic materials or inorganic materials. So now you have developed your material by using either of one or two or three of these techniques. Now, next very important question is the how to characterize those materials. So of course, the characterization of organic chemicals, organic molecules, let's say, is little bit different. Of course, it's not a little bit different. To be very honest, it's too much different compared to inorganic, and many times people get confused. So just to let's say re-emphasize towards young researchers and students how you can characterize them, and which characterization technique is, let's say, like mothers of those technique or mandatory to have in organic or organic. I will tell you later in the inorganic section. So in organic section, NMR is like a superlative technique to characterize the synthesized organic molecule. Then, of course, high resolution mass is also a very controlled, very precise technique. Normally, if a person let's say, researcher or student who is working on organic molecule synthesis, and then he has done NMR and high resolution mass, normally these two techniques are more than enough. And if you want to publish a paper based on synthesis, even just these two methods are more than enough. In some cases, of course, you can help or adds value to your work by having the carbon, nitrogen, hydrogen analysis also, which normally many people are doing in the organic synthesis. Then, of course, in some cases, if you want to really focus more on the functionalities of your molecules, you can do FTIR or Raman also. It will tell you a lot about functional group and functionalities of those molecules. But of course, like I said, NMR is a wonderful technique. Then HPLC and HPLC-MS, and then GC and GC-MS. To be very honestly, HPLC and GC are not the real characterization technique, but they are, let's say, helpful in certain way to let's say, recognize what your molecule is. But in general, they are not the independent characterization techniques. So in NMR, normally most common used NMR are proton NMR and carbon NMR. So in proton NMR, it tells you about the proton based on, let's say, it's based on the proton and the environment around the proton, or let's say proton environment around the proton. In carbon NMR, of course, focus on number of carbon present in the certain molecule in organic chemistry. So this is a typical, let's say, in general, how organic molecule can be, let's say, characterized by using the NMR spectroscopy. And you can see with respect to the magnetic field, how molecules or where the situation of the molecule can be. Roughly, let's say the aliphatic compound, the alkane, alkyne, these type of molecules, normally they appear on the NMR scale below 4. And normally organic molecule appear after 6 or 7 on the NMR scale. But of course, for the details, any student or person, they can go through the book and see in detail of the NMR and all those things. Even software are there which can, let's say, speculate the expected NMR data of your compound, and then you can compare with the real compound and all those things. But like I said before, NMR is like a mother of, let's say, it's a mother technique in organic synthesis or organic molecules, let's say. And if you are expert, let's say, a little bit in understanding proton and carbon NMR, to be very honest, you can be very much sure that you have synthesized your desired molecule. But like I said before, NMR can be aided with either high resolution mass or carbon, nitrogen, hydrogen analysis. So high resolution mass is actually, it's not just not the simple mass, but it gives you exact mass of the molecule. And normally that exact mass is in fraction. So let's say if your molecule is, let's say you have made a molecule where the molecular mass is 100, but normally in the high resolution mass, it would be something like 100.1045, something like that. In sometimes it's 3, let's say, figure after the decimal, sometimes it's 4. Normally it's 4 after the decimal, which are very accurate, and it pinpoint you the entire molecular mass of the compound. Then CNH, like I said before, it's like aiding technique. Still there's a debate. So I don't think so high resolution mass in Pakistan is present so much. Maybe 1 or 2 institutions only have this. So let's say a person has done NMR, so you can complement your NMR with the CNH analysis. So that would be also possible. If you have done CNH analysis with the dry compound, and then plus you have very good clean NMR, it's more than enough to have these two techniques to confirm that you have this certain organic molecule. Plus, like I said before, you can add Raman and FTIR, let's say more precisely FTIR, to also pinpoint the functionalities in your molecule. So these actually FTIR and Raman are more like laser-based technique. And then now HPLC and GC, like I said before, they are not like independent characterization technique, but people are using them mostly for, actually they are the analysis technique, but because certain molecules under certain condition have certain retention time, and then they leach out of the column of the GC or MS, GC or HPLC at certain, let's say, value. So you can really compare them with by running the standard, and then of course it can tell you that this is your compound which is coming out or eluting out of the column of the HPLC or GC. So that was all about the characterization of the organic molecule. And then now we move to inorganic molecule. There are actually different way to evaluate or characterize inorganic molecule compared to organic molecule. So in inorganic molecule, of course, simply a person can start by using SEM and TEM. Actually, SEM and TEM, SEM is scanning electron microscope, TEM is surface transmission electron microscope. They are more like imaging techniques, so they give you the images, let's say overview or morphology of the surface, whatever you have on the surface, nanoparticle, thin film, whatever it is. Then another technique is XRD technique, X-ray diffraction, which normally tells you about the phase or crystalline, let's say, nature of your material, whatever you are synthesizing. EDS is actually a bulk elemental analysis technique in which you just analyze the what kind of elements are present and also which proportion in your material. Then XPS, like I said, NMR is like mother of organic compounds. So XPS is like mother technique in the inorganic chemistry. So XPS is actually also an analysis technique which gives you the composition, but this composition is more on a very small scale. Normally XPS is a surface technique which gives you surface composition of 20, 30 angstrom. In some cases, people say it's more sensitive to 10, 20 angstrom depth of the surface. So it's not like a bulk analysis technique, but it's very precise to give you the surface composition of the material or the thin film. Then Raman people are using also Raman, but normally, if you have XRD, you don't need to use Raman. So now I'll tell you which technique. So let's say a person is making a certain molecule. So normally you need to have SEM and TEM. And then XRD is mandatory, and XPS in many cases also important. EDS is coming from the SEM instrument, so you don't need to do a separately. So within the SEM, you can have the EDS, let's say, facility, and then after doing the SEM imaging, you can just run the EDS, and it takes, I think, hardly 10 minutes to have one analysis. And also, of course, EDS, you can extend it to the elemental mapping also. I will tell you later on. So like I said, if you have done XRD, normally Raman is not required. But of course, XPS is a wonderful technique. So I recommend that any person working on inorganic materials, they should do these 1, 2, 3, and 4 techniques. And if you have Raman, of course, Raman is like a helping technique, further confirm the phase and let's say a little bit nature of your material, nanomaterial. SEM and TEM, like I said before, SEM is scanning electron microscope. TM is transmission electron microscope. Normally, transmission electron microscope is giving you image on a very fine scale. Let's say sometime even you can go to 1 or 2 nanometer scale. SEM, it's difficult, and then now of course we have this field emission SEM, FE SEM, which can give you resolution up to 50 nanometers. So even 50 nanometer particle can be 50 to 100 nanometer particle. Let's say can be seen with SEM, field emission SEM. This you can see a SEM image of copper oxide nanolith, and then here you see the TM image of the iridium oxide nanoparticle. And then here you also see these are all TM images of the zinc telluride. So you can see on different scales. So this is TEM image on 1 micron scale, and this is TEM image on 50 nanometer scale. So you can even see, because it's a more transmission, so it's not like a just surface analysis technique. So it's giving you inside nature also of the nanoparticle we have made. XRD, X-ray diffraction, like I said before, it's more like more to know about the real combination or real, let's say, construction of your compound in terms of its crystal structure and also the phase, what phase is present of the material. Like you can see, if you take calcium oxide and if you refine it, you'll see slowly as a function of temperature, it is changing and more, and with each temperature raise, you are changing its phase towards calcium oxide rather than calcium carbonate. And here you can see in this phase, because this is one of figure from our work, you can see how different phases can be seen. Normally, let's say because we were working more on the first order transition elements, And then of course in some cases silver and gold also. So you can see these different type of phases are present, and normally it's very difficult to really pinpoint these phases using other techniques. So XRD is helpful, and then of course XRD plus XPS in some cases can helpful to really figure out what kind of what is the phase of your material present in the material you have made. Then EDS, like I said, it's a bulk analysis technique, so it gives you the bulk composition of the material. Let's say if you have made a material combined, which is let's say coming from three metals, so it will tell you that there are three metals present plus oxygen in many cases come, and carbon also has a background, but it normally tell you about the nature. Let's say it's a quantitative and qualitative. So it tell you both about the type of element and also how much amount is present. But still, it's a bulk technique, so it's not like highly accurate, but still people are using it. Then, of course, you can extend this technique to elemental mapping. So let's say if your component containing sulfur, nitrogen, and carbon, so you can do elemental mapping, and then it can tell you the distribution of each element on the surface or on the particle that you are scanning for EDS mapping. Then we have the XPS, X-ray photoelectron spectroscopy. Like I said, it's also in the inorganic material. It's considered as the mother of the technique. So it really gives you the almost entire nature of your particle, whatever your particle or molecule, nanomaterial is. So this is like you can see it's a surface spectrum of whatever material you have, and then of course you can see high resolution spectrum of each element. So in this case, you can see it's a nickel. XPS for nickel, 2P, this is cobalt, this is copper, this is iron, and then of course because oxygen is these are all oxide, so elemental or metal combined oxygen is there, so you can see the different peaks for each oxygen, whether it's free oxygen or adsorbed oxygen, or even oxygen is bounded to which kind of metal. Let's say metal is present in +1 state, +2 state, or in some cases it is 0, which is metal, pure metal. Okay, now I'll quickly move toward, because I have taken already 32 minutes, let's say, because we started 3 minutes late a little bit. So quickly go towards the application. So we are focusing more, let's say my research is more focused on the application for energy conversion. So we are working a lot on water splitting, then of course CO2 conversion or reduction, light harvesting, electrochemical synthesis, electrochemical sensing, biomass conversion, in-situ spectroscopy or spectro-electeochemistry to be precise, and then of course wastewater treatment just as a side product and also side project, and also the electrochemical quartz crystal microbalance and nanobalancing technique. And we all do by using this molecular materials or nano let's say material, or in some cases the hybrid combination of both. So I will very quickly go. So we are focusing using renewable resources like sunlight and water and biomass. We have everywhere. CO2 again as a local commodity chemical, and then but just by playing around in catalysis, we want to make synthetic fuel from these resources using all the materials which I have shown you before in the previous slide. So in water splitting, like I said before, we make this organic molecule, we functionalize them on the surfaces, and then we form water splitting. In this case, you can see these are just molecules absorbed on the surfaces. They can also perform water splitting. And then these are electro deposited metal oxide. In this case, you can see nickel and cobalt. And they are, you can see from this figure, they are wonderfully well because they are performing for long duration of water splitting and without almost any noticeable degradation. In anodization, we have, in the beginning, we developed copper oxide nanofilms or nanoleaf films. By this method, and of course we also work on iron, silver also, and the other metals also. Spray pyrolysis, colloidal thin film methods, the solution and solid phase synthesis, molecular precursor method. And then we have molecular nanocrystals. These are very interesting material. Of course, you made them by using organic chemistry, electrosynthetic protocol. But the beauty of these type of molecule or nanocrystals, that they have ligand nature, which is organic, and inside they contain nanoparticles, which are actually just atoms of the molecule, atom of the element. And the beauty is that if you are really very having control over the synthesis, you can drop the size to even 1 or 2 atoms, just 1 or 2 atoms containing in the entire core of the molecule. And because their size is so small, so you can, of course, they can perform very specialized function, and they're huge application. In this case, we apply them for water oxidation. Then PVD thin film, palladium thin film, that was the first example, came from our group in 2019. It was a wonderful paper. And zinc, cobalt, telluride nanoparticle. Actually, these are zinc telluride, not cobalt telluride. So then some photoelectrochemical application, we develop those bismuth vanadate, hematite, and tungsten trioxide. We functionalize them with molecules. In some cases, inorganic material also. And you can see, yeah, in each cases, you can see the enhancement in the photocurrent, which indicate that during the presence of the catalyst, the current, the catalytic current can be really increased. And in some cases, even the onset potential is reduced. You can see in these cases, there is a charge suppression effect because the onset is prior to the onset of the simple photocurrent compared to the catalytic photocurrent. In this case, we are using different molecules on hematite. Then CO2 reduction also we perform. The CO2 we take as a commodity chemical because if you know the in roughly in an environment it's around 410 ppm. But you know if you calculate the or monitor the amount of CO2 in the region close to the powerhouses where they burn the fossil fuels, of course that amount is huge. It's many folds higher than the 410 ppm. And then beauty of CO2, if you have a very good catalyst, and then you can control over the electrode potential, you can really switch on to many product coming out as a result of CO2 reduction. In this case, you can see we develop this copper oxide nano hairs, and they perform, let's say, exceptionally well compared to simple copper oxide for reduction of carbon dioxide into syngas and also into formic acid. Okay, then of course in this case this is our recent work coming from collaboration work. So we developed this combined, let's say, composite material which is photosensitive, and then it's able to convert CO2 directly into methane gas. Of course, we also have performed the experiment for the reduction or the degradation of this 4-on blue dye also. Then biomass, of course, you can also, it's a like new emerging field in terms of catalysis, that biomass has, of course, huge application in many fields of chemistry, even beyond also. So in this case, we focus on two molecules from the biomass. One is the perfural electro-derived chemical, then other one is the sugar alcohol based molecules. So they can be blended together. So sugar alcohol can be converted into ethylene glycol directly, and this furan based chemical, which is the hydroxymethyl furfural, can be oxidized easily to make FTCA. And then if we combine these two, it will make the PEF plastic, which is let's say new alternative and good plastic for its common utilization compared to PET plastic, which is non-degradable and non-recyclable. Then in-situ spectro-electiochemistry, it's like this combination of two techniques. Actually, it is in-situ spectro-electiochemistry is a technique in which you can analyze or characterize whatever you are doing electrochemically by helping or taking aid of another technique. So in this case, we use the Raman spectroscopy, or precisely surface enhanced Raman spectroscopy. And then you can monitor whatever is present or happening on the surfaces. You can monitor it. Electrochemical sensing, we also started this project a few years back, and we developed this nano gold, nano texture gold film for sensing of iron, arsenic. And then of course we have this wonderful high surface area palladium thin films also, which are very good for sensing of many metals. So that was all, let's say quickly, all about what we are doing in research. And of course, like I said before, I try to emphasize more in terms of how we develop them, how we characterize them, and what kind of application are available there. Like I said before, they are materials beyond whatever range I have shown you. And they are, of course, there are a few more characterization techniques, but mostly these characterization techniques in organic or organic chemistry is used. And then, of course, application, more or less, these applications we are working on from time to time, but there are, of course, much more application you can have from organic or inorganic functional material or functional material. So in the end, I want to thanks to all my contributor places, labs and everything, because without money you can't do research. Money and freedom is so important. I was just lucky that many people were giving me money from time to time. And the freedom also to do work and switching from one lab to another lab and all those things. Also, thank you very much for listening to me. Thanks.
Thank you so much, sir, for such a nice lecture. Anybody, if somebody has questions, they can open their mic and ask your questions or discussion, anything. चलिए सर, जब तक कोई प्रिपेयर होता है क्वेश्चंस के लिए, I have few questions from your lecture. Okay, first of all, as you talk about NMR spectroscopy a lot, so I just wanted to ask that I'm pretty sure that there must be some nanomaterials which will not be soluble. Like for those nanomaterials, what characteristics characterization technique you prefer?
Sadia, actually NMR is more for organic molecules. So if you're talking
Yeah.
about organic molecules, of course, there are other way. I mean, if sometimes they are not directly solubilized, so you can indirectly do that. Or there is another technique which is like advanced of the NMR. It's known as solid state NMR or
हाँ,
SSNMR.
जी
So
जी
yeah, organic molecules, or let's say in many cases, the combination of organic molecule in the form of, let's say, aggregation or stacks, they can be characterized really very precisely by using solid state NMR spectroscopy also. And even in many cases, or pure inorganic molecule, some type of information can also be taken by using solid state NMR.
And you think that like the results which we obtain from the solution NMR and solid state NMR are like which do you think that more concise or precise?
If you ask me, because I mostly work, I think maybe one or two times I little bit work on solid state, but mostly during my PhD I work on NMR, and I work with my own hand. So I learned, I took the training and everything. So I think simple NMR for simple molecule, I mean the liquid NMR, solution based NMR, for not very complex molecule, but that's a relatively simple molecule, is much easy to do, and normally one analysis take only 11 to 12 minutes. And if you're expert, within half an hour you know whether you have made your molecule or not. It's really that quick, to be very honest, but it take time
Yeah,
to reach that level. 6 months to 1 year practice is required, something like
sure,
that. But then of course it's just
sure.
like, just like click of your hands.
It must be. Anybody has some other questions? Well, sir, I have seen some papers on water splitting in which you have used artificial leaves.
Mm-hmm.
So I just wanted to ask that for those artificial leaves like molecular nanoclusters, you people just use transition metals or some other as well?
If you are talking about entirely the artificial leaf has
Mm.
three components.
Mm-hmm.
Two, at least two component, but in many cases three component. One component is the light harvester part. So light harvester part can be organic and can be inorganic.
Okay.
Okay. Then you need a, let's say, system where you can transfer the material which is in water splitting proton, and in some cases hydroxyl ion also. And then you also need
Mm-hmm.
a let's say channel where you can transport the electrons. And then second part or third part is where you want to reduce something or oxidize something. Let's say if you are making hydroxyl ion, so you have to make water out of those hydroxyl. You have to make oxygen out of those hydroxyl ion. And if you are making
Mm-hmm.
proton, which is normally happening in water splitting also, you need to take them to the reduction side where proton can be directly reduced, like in clay midomonas and hardy, and also in
Mm-hmm.
nostoc. So they directly reduce it to make hydrogen. But in higher plants, like we see green leaves, green plants outside, they combine this proton with CO2, and then they make the glucose molecules for the plants. So this is the concept of an artificial leaf. Because I was working on it, that's why I know. I mean, it's let's say it's taken like this. In some cases,
Okay.
artificial
It
leaves
means
have
that
a membrane barrier also, but some people sometimes they don't use a barrier to separate the anode and cathode, or let's say reduction and the oxidation sites.
so it means that it could be if it's both organic and inorganic, so it could be metallic and non-metallic as well.
Yeah, of
The
course it can
inorganic
be. Yeah,
part.
yeah, yeah. People
Okay.
are already working on tandem combination or hybrid combination. Even two or three papers we have also on this combination where we use the inorganic semiconductor as photoelectrode, or let's say light harvester, and then we put an organic molecule as a catalyst.
Mm. All right. Thank you so much. Thank you. If somebody has question, you can open your mic. You're free to ask questions.
I think people are sleeping maybe, so we can wind up.
No, it was a nice talk. Really, I
Thank
I
you very
again
much.
want to thank you. And one more last thing I want to ask. So, being like so much into the research of water splitting, where you are seeing the future of water splitting in Pakistan? I mean, do you
Future,
think
to
that
be
it
very
can
honest,
be commercialized?
yeah, yeah. To be very honest, I still remember in 2015 or 14, first time I gave a lecture on water splitting. And that time, no
Mm,
one was so much interested, but it was something new for people. But then in 1 year,
Sure.
few groups started. So in 16, 15, 16, few groups started. And now I see almost in every university, there is someone from physics or chemistry department working on word spreading. And I'm so much happy for that, that people are working on it. And you will also see, I mean, if you follow the research output in Pakistan, you will see so many papers are also coming on word spreading from many, many groups in chemistry and physics, even in material science also, chemical engineering also. But of course, the thing is, like, to, let's say, pinpoint your the answer of your question. I think people are still only, they are busy, let's say, or their focus is only to make paper. They are not going to the next stage, which is develop the device, and then going to, let's say, taking to the commercialization phase, where we can make, let's say, hydrogen from just using solar energy and a cheap catalytic material, or renewable energy.
Okay.
So wind energy is also renewable. Even our hydropower are also renewable energy sources.
So it means like you are one of the pioneers of water splitting in Pakistan.
I won't say that like this, but of course, at least let's say I have introduced this field in Pakistan.
Sure, sure. Okay, somebody has question. Anam Yasi. My question is polyurea and polyurethane can be synthesized through above mentioned process? Question mark.
Polyurea, these are
Polyurea.
polymers. Yeah, these are polymers. And normally polymer follow a different, let's say, synthetic protocol. But I know, of course, you can use not maybe polyurethane and polyurea. Electrochemical method can be used to make electrochemical polymer like polyaniline, polythiophene. They are developed by electrochemistry. But I think polyurethane and polyurea more like they follow the polymer synthetic protocols, which are a little bit different. But in general, they are also like sort of organic synthesis method, in which you just add the initiator to initiate the chain, the radical formation, and then they just follow the chains, and whatever the length of the polymer, length mean the molecular mass of the polymer molecule you want to make, you keep on it running, and then at some stage you have to just stop the polymerization, and then you have your polymer ready, whatever the molecular mass is.
Thank you so much, sir, for
Yeah,
your
thank you very much,
time, for your
Sajid.
efforts. Thank you. So this is the end of session. Thank you very much for joining, everyone.